Hello and welcome to this week's Retrieval Market Demo Day. Today's date is Wednesday, the 25th of May, 2022. We've got a great schedule today. We've just got the one speaker, which is George Nee from Magmo, speaking about the multi-hop payment channels for the Filecoin Retrieval Market. If you have any questions, please add them to the Slack thread so we have them into perpetuity. And over to you, George.
Thanks, Patrick. As Patrick said, I'm George. I'm part of the Magmo team, and we've been working on multi-hop payments for the Filecoin Retrieval Market. So I'll just jump straight into it. I'm hoping to keep this kind of informal, so I'm happy to be interrupted with questions as we go through, or through the chat, whatever you'd like to do. Let's see if I can get my next slide. There we go. So the outline of today's talk, I'm going to just intro the team a bit and try and describe the problem that we're trying to solve. And then I'm going to give an overview of our solution, which is all based around something called virtual channels. And then I'm going to do a bit of a deep dive into what we've actually built so far, which is this Go Nitro module. And then I'm going to wrap up with a look at what we're going to be doing next. So who are Magmo? We've got some of the team on the call today, Andrew and Colin, I can see. We're 5 developers inside a consensus mesh. We've been working on state channels for a number of years. We maintain the statechannels.org site, and a lot of our code you'll find under that GitHub namespace. So we've been working with lots of other state channel teams, mostly in the Ethereum ecosystem. But we kind of dug into Filecoin and realized there was a really compelling use case for our particular flavor of state channels. So that's what we've been working on most recently. So if you go to statechannels.org or magmo.com, you can find various goodies that we have produced over the years, such as blogs, research posts, documentation, white papers. One of the things we did relatively recently was a Web3 torrent application. So this was a state channel application we made as a kind of proof of concept in TypeScript. And with this application, you can earn cryptocurrency for seeding files, for uploading files for other people to download. So our heads were already in this kind of incentivized file delivery space. So that's why hopefully the segue into the Filecoin retrieval market, we've got a bit of a head start on that stuff. Yeah, so the actual problem that we're trying to solve is that the Filecoin retrieval market requires low latency micropayments between retrieval providers and clients. And that's not something that's really available today. So if you're to use a vanilla payment channel, you need to do an on-chain interaction every time you want to connect a new payer and payee. So there's a high latency, expensive cost to setting up an on-chain interaction. Now there's something called a multi-hop payment, which doesn't require that on-chain interaction. And I'll explain a bit more about how that works. But that's also something that's not available on Filecoin yet. So that's where we're going to come in and provide a solution. So some of you may know more or less about payment channels, but I'll try and explain from the ground up. There's something called an HTLC approach, which is used in the Lightning Network on Bitcoin. And the way that works is, instead of Alice and Bob, who want to have this payment relationship, starting a new channel on chain, depositing funds on chain and using that to pay each other, they use a pre-existing channel that they each have with some intermediary who we're going to call Irene. Sometimes I'll call Irene the hub or the payment hub, but someone sits in the middle of Alice and Bob and helps them to pay each other. So in the HTLC approach, effectively what happens is Alice pays Irene and Irene pays Bob, and those payments are locked together or unlocked by the same secret revelation. So they're atomic is the idea. So you can see Irene sitting in the middle. She's got 3 coins in step 1. So time goes down here. This is like step 1, step 2, step 3, step 4. Irene's balance stays the same, but Alice's 3 coins each get transferred through Irene to Bob. So money's moved from Alice to Bob through Irene. Irene's balances remain constant. A small extension to this that you can imagine is that Irene actually is creaming off a little bit of service fee as she passes the coins on, so she can get incentivized to provide this service to the network. So that's kind of how it works in Lightning. And it's a great system. You can have multiple hops in here. You can have Ivan, a second hub or a second intermediary sitting in there, and exactly the same thing can happen. You just have to lock more payments together in an atomic way, and you can get that to work. The big downside here is that Irene and Ivan, if they want to spin up, large provider service to lots and lots of Alice and Bob pairs in a very kind of healthy, large-scale retrieval market, they're going to have to do a lot of work. They're having to process every single payment. And what we're really hoping to achieve is micropayments, meaning very small amounts of money moving with very high frequency. So there might be a small amount of cryptography to do on every single micropayment. That means these hubs have to do a lot of work, considering they're going to be having a lot of connections to the sort of end users. So that's something where virtual channels can come in, which I'll explain in a minute. And that takes all of the load off of Irene and Ivan, or almost all of the load off them. And that's something that Magmo specialize in, virtual channels. So our solution, and I've just lifted this from our grant proposal, just to sort of like hold us to account there, is a set of executable protocol specifications that implement the off-chain component of an efficient multi-hop payment channel protocol, as well as some glue code that makes it all work. So efficient here is going to mean this low latency idea, and the idea that those payment providers in the middle, the intermediaries, aren't having to do so much work. So how does the virtual channel approach work? Well, I'm skimming off a lot of details here, obviously, but it works a little bit like this. So Alice and Irene and Bob have got the same actors. The same people want to pay each other, and Irene is still there wanting to provide a service to allow these people to connect without having to go on chain. And the difference this time is that they are going to execute a joint protocol, which we call virtual fund, where they all have to send messages and do a little bit of crypto and signature recovery and that sort of thing. But once they've done, Alice can send money directly to Bob, and Irene doesn't need to know about it. She doesn't need to see the messages. She doesn't need to verify them. She only gets involved right at the end when they're finished. So you can see there that Irene's very happy now because she's got a lot lower load on her machine, on her services. And again, this will equally work with 2 hops or more than that, depending on who you're connected to. So we actually think 2 hops is kind of interesting. Alice might be connected to Irene, her payment provider in Europe. Bob might be connected to his payment provider, Ivan, in Asia, and Irene and Ivan will need to be connected too. They might have a very sort of big, high traffic connection, intercontinental connection. And if you had something like that, you could imagine, across the globe, people wouldn't have to have too many hops to get to someone with a file that they want to pay for to be retrieved. So I just have this little visualization to try and explain that a little bit more. Folks might not be able to see this very easily, but I hope they will. So there's some very faint lines on here, which might make it hard to see, but I will just try and explain what's going on. The current payment system, if you like, so we've got retrieval providers here on the right-hand side, retrieval clients here on the left-hand side. The providers have the files. They're going to be uploading them to the clients. The clients will be sending payments back to pay for those files. This big circle here is supposed to represent the blockchain. And what this visualization is showing, that under the current system, when a client connects to a provider, they have to go on chain, and you might or you might not see little red flashing lines connecting the clients to the hub. Sorry, not to the hub, to the blockchain. That's what this big circle is. So those are the kind of high latency operations that we really don't want to have if we can avoid it. So once you start putting intermediaries into the mix, you still have to use the blockchain to set up connections between clients and hubs, and providers and hubs. But then after that, all of the messages are off-chain. So you just see flashes between these connections here. They're not going to that high latency blockchain. They're relatively low latency. And as I tried to explain with the virtual channel approach, not only are we taking load off of the blockchain, we're actually taking load off of the hubs as well. So it becomes a really fast peer-to-peer process between clients and providers. And yes, we're envisaging like kind of large scale networks with lots of connections here, and that's what we're trying to service. So how does the virtual fund off-chain protocol work in a bit more detail? It works a little bit like this. Don't worry if this doesn't make too much sense, but I'll give it a go anyway. So we've got our same actors, Alice, Irene, and Bob here. We start off with Alice and Irene and Bob each having a two-way channel. We sometimes call that a ledger channel. It's like sort of long-running connection with a decent amount of cryptocurrency backing it, stored on chain. And Alice and Bob want to pay each other directly, as I keep saying, without opening a new channel on chain and depositing more money. So what they do is they set up a three-way channel with this intermediary, and then they each update those existing two-way connections to pay money into this new three-way connection. So instead of that channel paying money out to end users, it's actually paying to another channel, which is a three-way channel. And once they've done that, everybody can agree to sort of cut Irene out of the execution of that channel for a length of time. And then, as I mentioned, Alice and Bob, well, Alice in this case was going to send money directly to Bob. In this case, it just sends one coin, might send 1,000 micropayments or something like that. And when they're finished, we can defund the channel virtually, which you can see happening here. So that, in this example, it's one coin. When the channel is defunded, you can see the individual two-way connections are resolved in the following way. Alice has one less coin, Bob has one more coin, Irene has got one more in this connection, one less in that connection, and overall she's neutral. So that's how virtual channels work. And that's our job in this project so far, is to write the off-chain code, which will send all the messages, do all the signatures, that will enable this to happen securely and enable it to happen in a way where Irene, well, none of these actors' funds are ever at risk. So if any actor starts behaving maliciously or stops responding, we've designed our protocol so that there's always a route to every participant getting their funds back in a fair way. So here's another complicated diagram. I don't want folks to look too closely into this one. It's not super important, the details, but this is just an example of how we start designing these protocols on pen and paper, as it were. So we have these messages that get sent from one actor to another one. This is Alice proposing that virtual channel, and a bunch of other messages get sent. And by the end of that, we hope that we've got a funded virtual channel ready to make payments. That's how it should work in principle. And I'm going to return to this in a minute once we show you what the software does, and we can compare an actual execution back to this diagram and see if we've kind of lived up to our own plans, if you like. And the sort of spoiler alert is that this part here, where we fund, so this step here where we fund the three-way channel using these two-way channels, turns out to be a bit more complicated than you might imagine on first go round. So there's going to be more messages required here. So what have we built so far? Well, we've built a Go module called Go Nitro. It's not really ready for production usage yet. That's what we're going to work on next. But it's a really nice like proof of concept testing ground for all of these things. We've concentrated so far on having these virtual fund protocols working off-chain. And that's the killer feature. That's what we're concentrated on. So at some point in the future, in the near future, we hope this will become much more like something that will be ready to integrate it into another retrieval market project, and we should be able to get payments running in those virtual channels. So, and here's just a flavor of what the API currently looks like. It's not a brilliant developer experience at the moment for someone consuming this code, but this gives you an idea, I think. So this is taken from one of our integration tests. There's a whole bunch of setup, but essentially you have to spin up a Nitro client here. You have to pass in some services like messaging, something that talks to the blockchain, some kind of storage module, and some logging. And then you're going to call Nitro client.create virtual channel, passing in all the data that's required for that. So I want to interact with a certain counterparty. I want to go through a certain intermediary. and I want a certain amount of money in that channel, and so on. That's what we have at the moment, and we can test that all out, and it works really well. In the future, as I mentioned, you will get a response here, which is a virtual channel ID, and you'll be able to use that to make payments. So just a little bit more detail, because I promised a deep dive on what you'll see inside our code base. There's kind of two parts to this. We tried to build our system as a functional core with an imperative shell. So we've got a large amount of functional code that's implemented as pure functions. And then we've got a relatively small amount of imperative code that actually does stuff. So if you go in the protocols package, you'll see all these things like virtual fund, virtual defund, and each one of those is an attempt at an executable specification. So it's trying to describe the messages that need to be sent in order for this protocol to be successfully executed. And it doesn't actually do anything, it just describes what should happen. So there are these two methods, update and crank. And crank is really the interesting one. It takes your store, your selection of states that you've got in your client, and it computes like what the next thing to do is effectively. It might declare a message that needs to be sent, for example. So again, I'm just waving my hands a little bit here. You probably won't get the full idea of exactly what's going on, but we've designed these cranks as pure functions that follow a sort of flow chart. So every time you crank an objective, you're trying to make progress on a protocol. So you're going to flow down this flow chart, and you're going to keep asking questions about your data that you have. And if you're stuck, if you're blocked on another party performing some kind of action, you might hit one of these exit points. Sorry. And then eventually the data will come in from a counterparty, and you'll be able to get over that hump and onto the next thing, and you'll keep flowing down here until the protocol is complete. And this, as I said, is implemented as a pure function, so it's relatively easy to test without having to spin up lots of fake databases and all that kind of thing. And then the other part of the story, the other layer of the onion, is this imperative shell that we've built. So this gives you a bit of an idea of like how this all fits together. I showed, sorry, this keeps jumping around. I showed the API of our software, which is this line over here previously. So there's a number of things that happen when you call an API method. The consuming application makes that call. It gets sent into the engine on a Go channel. The engine's then going to fetch any existing data that's relevant from the store and bring it back. It's then going to do one of these cranks that I mentioned to decide what to do next. Those cranks declare side effects, which might be something to send to the blockchain, like a blockchain transaction. It might be a message to a peer. The engine's going to execute those side effects and then recommit the data back into the store. And then it might also send a message back to the application. We recently added this little arrow, which is interesting. So when the engine makes progress on one objective that it's trying to achieve, one of the side effects can be that it's unblocked a different objective, so it can go around again and make more progress on something else. And that's kind of interesting. Yeah, so those are the components inside our software at the moment. And I promised that we could look at an actual execution and compare it to our sorry, Patrick's just asking a question. Does that mean crank calls crank? Yes, crank doesn't actually call crank in the kind of call stack sense. That's one way it could happen, but we recently changed it. So what crank does is it schedules some more work that will get cranked at some later point. So it's a slightly more asynchronous thing, but yeah, that's effectively what happens. Yeah, so what we're going to look at next is how the executions actually play out in reality compared to the way we designed them. So we can look at that in the following way. We run these end-party integration tests, and that's how we're testing everything at the moment, and it all happens inside a single process. And one thing that we've been having fun with is instrumenting our clients with vector clocks. So that means that when all these messages are getting sent around, we've used a library that we found that will wrap the messages in these little counters. And there's a vector clock algorithm that runs between all the participants. And they're basically counting events and running a little algorithm on top of everything else that we're doing. And that enables us to infer which events came before which other events, get a partial order. And that means we can go to this website here that makes nice little visualizations from the logs that get output by these instrumented clients. So this thing on the right here is, I've got 3 actors. I should have probably written Alice, Irene, and Bob, but I've used more retrieval market terminology here. So there's RP, retrieval provider, PH is a payment hub. So that's our kind of new actor that we introduced to get our virtual channels going across a hop. And RC0 is a retrieval client. And what's happening here is a message is being sent, is being broadcast really from this client to the other 2 players. That's a kind of proposal that they want to open a virtual channel. And you see a response in kind from the other 2 actors. So this is broadcasting to the other 2. This is broadcasting back to the other 2 saying, yes, we all agree this is something we want to do. So that's a very basic motif you can see. And that happens exactly as you would expect it to. So I hope that makes sense to everyone so far. The next thing we can look at is funding a virtual channel. So this happens also exactly how you'd expect it to do. It's a bit complicated. It looks a bit complicated, but what's actually happening here is on the right-hand side, once everyone's agreed to fund this virtual channel, the retrieval provider messages the payment hub to say, let's fund this new channel. And if we ignore what's happening on the left, we get a response here. And as soon as that's happened, this V1 message goes out, which is saying, from PH and RP's point of view, that virtual channel is funded and we're good to go. The same thing happens on the other side. The retrieval client talks to the payment hub and says, hey, why don't we fund this virtual channel? Down here, the payment hub's saying, sure, let's do it. And then once these messages have been exchanged, we swap this V1 message over again, which is this confirmation that the virtual channel is ready to be used. So again, that happens kind of pretty much in the way that you would expect it to. Just a little aside here on the partial order of events that we see here. So what I did next with this little experiment was to increase the number of retrieval clients. So I've still got 1 retrieval provider. I've still got 1 payment hub, but I now have RC0, 1, and 2. So 3 clients, maybe they're all trying to get the same popular file from the retrieval provider. So they're all trying to spin up a virtual payment channel with the same retrieval provider through the same hub. And once you set up a system like that, it starts to get a little bit more interesting. So you can see here these proposal messages. In this visualization, there's no sort of temporal ordering between them. We can't say which one really happened first. But by the time they get into the other players, there is an order. So, and they cross a little bit here. So the message from RC2 happens first, then RC1 is received first, then RC1 and RC0. That could have happened in a different order. We can't build our system in such a way that it depends on the order of those messages being received. And that's something that's taken us a little bit of time to sort of engineer a solution for. So yeah, what I'm going to do next is go to the actual visualization software, which is a bit nicer in the browser here. So I mentioned that things don't exactly play out the way you might imagine here. So these proposal messages up here aren't super interesting. What is the interesting bit is down when we get to here. So let's have a look at these 2 messages. So what we have, as I mentioned before, is 3 clients all trying to connect to the same provider. And what that gives us is competition. It gives us a lot of traffic in the connection between the payment hub and the retrieval provider. And we realized that that is a potential problem because our system is such, and probably any simple system, any payment channel system is such that the order in which these virtual channels are funded is really important. They can't happen in any order. It has to happen in a consistent order on this machine and this machine. So they somehow need to synchronize what they're doing. They can't just do it in a completely asynchronous way. So our solution to that is to send a little bit of extra information the whole time. So the first message that gets sent here is that the provider is proposing to the hub that virtual channel V2 is funded. So V2 is the channel that connects RC2 with RP. Sorry about all the acronyms. But there's a virtual channel trying to be created and funded between each of these clients and the provider. So this message is saying to the hub, let's fund V2. This message is saying, let's fund V2, then fund V1. And this one says, let's fund V2, then V1, then V0. And because we never get a reply, like the retrieval provider is kind of impatient. It doesn't get a reply to that proposal. So it sends the next one. And then it sends the next one. And each time it sends a new one, it sends all the previous proposals as well. And having that redundancy in there enables us to synchronize what's going on and make sure both parties include all of those funding requests in the same order. So that was pretty complicated. So if you followed that, I'll be really happy. But I can have another go explaining it if people didn't quite understand. So yeah, that's. Can
I ask a question on that one?
Yeah, please do.
Just jump in. So just to say why that's needed, is it because if you've only got a certain amount of funds between the payment hub and the RP, so if you've kind of maxed that out on the first channel, then the second two aren't going to be able to be created. So you have to be able to only send in ones like below your payment limit.
That's exactly it. There's actually a couple of reasons. There's some other reasons around the fact that we'll very often end up like hashing the list of virtual channels on chain. So if the order changes, it might not mean anything semantically different, but it might end up giving us a different hash. That's not super important. What you said is much more important, which is like, you know, if you take your credit card out and you want to buy 3 expensive things, you need to like decide which one is getting paid for first, because you might not have enough money to cover all of them. So that's basically the fundamental reason. Yeah, you hit the nail on the head.
Well, actually, I had a question on that too.
Yeah.
So, I mean, I can definitely see from a point of like fairness and for humans to be able to understand what went wrong if funds run out, it's better to like do them in order, right? So, so I can definitely see that. Beyond that, I mean, if you really didn't care about making it kind of comprehensible, it doesn't matter which channel fails. Which request fails. Like it could have been that the most recent one in kind of a last in, first out one is the one that gets funded, and then the earlier ones fail. But yeah, I could see in that case, everyone would be kind of scratching their head. They're like, we had money when we submitted it, and then that one failed, but one later succeeded. So I mean, definitely I think you headed off from having people trying to wonder what went wrong in the case of errors, which is definitely valuable to do. Debugging errors is actually like the most important part of getting a system to work. So make that easy.
Yeah, that's right. We do have some other ideas, actually, to be fair, around doing some of this stuff in a slightly different way, which wouldn't necessitate this system that we have now. We've actually spotted, using this debugging system, we've spotted that our messages are actually growing at the moment, which is a bit of a problem. So the more clients we have, the bigger our messages will get if it's this kind of topology here. So that's something we need to revisit. The messages should grow a bit and then start shrinking, but they're not at the moment. So something we need to look into. Yeah, so this is pretty much the end of my presentation, really. So the main things I want to sort of signpost that we're going to be doing next is essentially features and performance. So big feature we don't really currently support is actually doing payments, and we need to test that out. We also want to have channels with real FIL in them. So at the moment, we've got a lot of mocks around the blockchain. We don't have real assets being deposited. So we're going to hopefully be working with the FEM team to try and get our on-chain code fully written and deployed so we can use real Filecoin. Another thing we need to do is to have a recovery protocol. So I mentioned that we design things so that all participants can get their money back effectively. We don't have the code that enables to do that. We can wave our hands and say there's everything in your store needed to do this, but we actually want to write a protocol so your wallet's like, so your Go Nitro client is really like looking out for you and enabling you to recover your funds if that should happen. And then there's some performance things you want to look at. So things like crash tolerance. If you need to restart your computer, can you pick up where you left off? Getting the time to first payment down. So in a very basic model where you have the payments and the retrieval going on, you might say, I need to have my payment channel set up before I start doing any retrieval. And because that's such an important metric in the retrieval market, that translates for us into what we're going to call time to first payment, which is how quickly can we get this virtual fund protocol to be completed. And that's going to depend on the number of network messages, which we might be able to optimize a little bit, the amount of crypto that goes on, things like concurrency control inside the payment hub. We'll be working very hard. So we plan to deploy a sort of test network where we can start measuring these things and trying out different optimizations and basically getting the whole thing ready for integration. And yeah, if anyone wants to reach out on email or in the Slack, my details are there. And yeah, we can do questions now.
Yeah, I mean, I'd say on the time to first payment, since I feel like, Patrick, that's probably on the Filecoin side going to be considered, anything around latency on a retrieval network is going to be considered super important. My suspicion here is that, like, especially if this network ends up being between kind of secondary retrieval market providers who are a little bit better known and maybe not end users, there may be certain types of users that retrieval providers in the Filecoin network are willing to start sending data to while the payment is being set up. So that'll be interesting to kind of explore, to like what extent there's some reputation system that allows another 5 or 10 milliseconds to be shaved off the process.
Yeah, for sure. I think that, yeah, we definitely do some kind of pre steps just to try and get that time to first byte is essentially what we're trying to minimize in the retrieval networks. And if we can make that independent, or at least not definitely longer than time to first payment, then that'd be interesting to look into. There was a question which I remember speaking about a few months ago, and just be interesting to hear what your thoughts are on it now. We spoke about how this is like two-way payment channels. So Alice and Bob can make micropayments to each other. Quite often in a retrieval network, we've got clients, let's say it's a browser, who is only going to be on the retrieving end in terms of the data and will be making the micropayments. If we did one-way virtual payment channels, would that reduce the number of steps or round trips that have to be made before you can start doing your payments?
Yeah, I think the answer is yes. I don't know if Andrew wants to jump in on this because I think he knows this best, but I think that there are optimizations that we can make that by leveraging that assumption of a unidirectional channel. And yeah, that seems to totally fit the use case here. So that's definitely something we'll look into. If it's, I suppose that's why I'm keen to get this like testing set up with, first thing, because we need to know sort of how, how much of an axe we need to take to different things, or how hard we have to try in different areas to get that latency down. But yeah, that's definitely an avenue we can go down. Andrew says he's, I think he's in his construction zone. So.
Cool. Yeah. Any other questions?
I'll just in terms of optimizations on unidirectional payments, Patrick, there is another one that we can definitely do, which is the storage of the payments themselves. So payment will be something like a digital signature plus some other data. If you're sending payments, you're decreasing your balance. So you don't really need to store those payments. They're not critical to you. When you're receiving payments, it's more important that you save them to disk in case you need to take them on chain. So that's another example where you can like save some disk space effectively, or save some IO operations if you don't need to receive any money.
Okay, yeah, Andrew's coming on the chat, which I'll read out loud. The main intuition is if Bob doesn't deposit funds into the channel, then Bob doesn't need to sign off on any changes to any outcome changes. when setting up the virtual channel. So yeah.
Yeah, that makes sense.
Oh, and some more. As long as the rules of the channel enforce that Bob's balances don't decrease during these setup actions.
Yeah.
Cool. And then, yeah, I just have one final question, which is, you mentioned that there's the whole kind of crank decision tree that you've got of how far through you are. Is any sort of, you said it was like that you'd written it as like pure functions. Is any state, does that mean that you're not holding any state about how far through the crank you've got? When you do a crank, are you starting from the top of that decision tree every time and working your way through?
Yes. So yes and no. So how we previously approached this problem, let me bring up the slide, is to have something more like a traditional finite state machine. So, you know, boxes with named states and transitions between them. And we modified that a little bit to end up with this. And the reason we did that is because we have like what I call extended state, which is like your big old bag of data in your store, like signatures, private, you know, lots of extended state that's potentially infinitely big. And we didn't really want to put another layer of finite state on top of that. So you might have a finite state that's like, I am waiting for a message from Alice. But really, you can tell that just by looking at all this extended state, by looking at, I don't have state number 0 with a certain signature on it. So instead of having a finite state machine, we just have this big old bag of data, and that does get updated each time we do a crank. So state is being updated, but it's not like a finite state with a name. It's just like some states might get a signature added to them. And then we do another crank and we look at that set of data. And these kind of pause points kind of play the role of finite states, but we don't actually save them, and we don't actually have any logic that depends on them. They're just kind of like almost like debugging information. They tell you where you've got to, but we don't really use it. Does that answer your question?
Yeah, it makes sense. Cool. Thank you.
Cool.
Well, yeah, any more questions? More thoughts? Nice. Well, I'll stop the recording.